Let's talk about mechanisms. So at the beginning of this lecture, I told you that when you have more than one kind of reactant, you can actually undergo a series of steps that lead up to the product. And so the reaction is not so simple as to say A plus B give you C. You might actually have a series of steps in between that ultimately lead to product formation. So for instance, if we look at the reaction right here, two NOs reacting with F2 to give you two FNOs. The idea is pretty much that when you do reactions, you could think of these things as collisions, elastic collisions of two particles that come together. And statistically speaking, it is likely that two different objects can come together with the right energy to basically provide a collision that has enough energy to surmount the activation energy. But to have three or more objects colliding at the same time in the same region of space with the right orientations and the right energy is very unlikely to happen. So technically speaking, when we have a reaction, we try to break this up into elementary steps that contain only two molecules or only two atoms reacting with each other. So instead of having two NOs reacting with one F2, the first step could actually be one NO reacting with F2 to give you FNO plus a fluorine atom. And in the next step, that very same fluorine atom that has been formed can react with another molecule, a second molecule of NO, to give you yet again FNO as your molecule. And so one thing you're going to notice here is that the fluorine atom that was formed got consumed in the next step. And if you add up these equations together, what you're going to find out is that F cancels out entirely, meaning that the fluorine atom is actually an intermediate. It gets formed in the course of the reaction, but in that very same reaction, it gets consumed right away. So it never acts as a full-on product or a full-on reactant, but it is invoked to exist to yield the final product. And if you continue adding the elementary steps, what you end up finding out is that the addition of the elementary steps yields the overall reaction that we had to begin with. All right, so the thing about elementary steps is that they themselves represent individual reactions with individual rate constants. And the way you basically write the rate laws for each one of these elementary steps is actually rather simple. All you do is look at the reactants and the coefficients associated with the reactants, and you simply multiply the value of the rate constant by the concentration of that reactant raised to whatever coefficient you see. This is to be contrasted with the situation of the overall reactions, where you do not use or assume that the balancing coefficients are the exponents of the rate laws. You never assume that for overall reactions, but for elementary steps, you literally make that assumption. So the rate law of the first reaction is simply K times concentration of A to the first power, right? Because you only have one A present in here. For the second reaction, oh, and one more thing, the molecularity of this reaction is said to be unimolecular because you have an order of one for the reaction. Now, if you have two molecules of A reacting with each other, then the rate law of this elementary step will be K times the concentration of A to the second power because you have a balancing coefficient of 2. And the molecularity of this will be said to be bimolecular, or have a molecularity of 2 because the order of the reaction is 2. Now, if you're reacting two different molecules or two different atoms together, the rate's law is going to be K times the concentration of A times the concentration of B, each one of them raised to the first power. If you add the exponents of these two molecules, you're going to get 1 plus 1, which is 2. So the molecularity is also 2 for this reaction, even though you have different molecules. For the next reaction, you have three molecules reacting together. The molecularity will have to equal 3 because now you have K times A to the third power. This is a situation that is not very likely to happen because you have now three things colliding in the same spot with the right energies, the right geometries, the right directions to make the reaction happen. And that is not very likely to take place. Same idea with your A plus 2Bs. That's three different molecules, not very likely to happen. The molecularity is equal to 3, meaning that this is a ternary reaction. And then for the last reaction, you have three different components, which multiply together give you a molecularity of 3 as well. So um, in all these cases, you're dealing with a ternary reaction, which is not very likely to happen, but there are some examples out there where it has been proven that yes, thermomolecular reaction is indeed what's happening in terms of the elementary steps. All right, now for the rate law, what we're going to do is take account of the elementary steps of the reaction and derive a rate law, which ultimately has to be compared to the experimental rate law of the reaction to see if your mechanism makes sense in terms of what the experimental data is providing you with. So we're going to go over uh, this particular set of steps. So looking back at the original reaction, two NOs reacting with F2 yielding two FNOs. You have the two following reactions, uh, reactant going directly to product, reactant going to product. You have rate constant 1 and rate constant 2. And the rate law for the first reaction is K1 times NO times F2. The rate law for the second one is K2 times NO times F. All right, so the way this goes is that you have to be on the lookout for the slow step, because the slow step is what's going to determine how long it takes for the reaction to finish or to go forward. And by default, it will determine how long the rate is. So if the first reaction is the slow step, automatically the rate law is going to equal K1 times NO times F2. And since NO and F2 are actual reactants or products present in the overall reaction, this is it. This is the rate law of the reaction. There's nothing else that needs to be done. All right. And in terms of your relative rates, because of the balancing coefficient, half of the rate of NO is equal to the rate of F2, which is also equal to half the rate of FNO. But that's basically equal to the rate law that you're actually obtaining right here. Okay, so the rate law is basically equal to the average out rate of the individual components of your reaction. All right, now let me show you another example. This is where it gets a little complicated. We have a reaction between H2 and Br2 yielding 2 molecules of HBr. The mechanism is actually a lot more intricate than you would expect, because what happens is that Br2 reacts to basically break its own covalent bond and yield 2 atoms of bromine. And this reaction is said to be in equilibrium, meaning that it can go forward, but it can also go backwards. And the forward process has a rate constant. The backward process has another rate constant as well. All right, but this type of arrow going back and forth is what we call an equilibrium arrow. And what this tells you is that you have two steps that you're going to have to be on the lookout for. Then the bromine atom reacts with H2 to give you HBr and hydrogen atom. And in the last step, hydrogen atom reacts with another molecule of Br2 to yield yet one more molecule of HBr and produce Br atom in the process. So for the first reaction, the rate forward is K1 times Br2, which is the reactant. The rate backwards, which is basically going from the two Brs back to the Br2, is going to be K minus 1 times the concentration of Br raised to the second power. This third reaction is simply K2 times Br times H2. And the last one is going to be K3 times H times Br2. These are all the rate laws that you can derive for every single step present in this mechanism. Now, you need to be told what the slow step is in all these processes. Otherwise, you really don't know where to go in terms of determining the rate law of the reaction. For this reaction, it so happens that the third reaction is, or the third step of the elementary sequence of steps is the slow step. And that means that the rate law is equal to K2 times monatomic bromine concentration times H2 concentration. The problem with this, however, is that you cannot just leave the rate law like that, because Br atom is not any of the reactants or any of the products present in the overall reaction. So what we're going to need to do is use some of the other relationships here to substitute for the concentration of Br2 such that we end up with only products or reactants in your rate law. All right, so yes, to leave it the way I have it right here is not sufficient. We're going to need to do something else. And here's where the equilibrium actually comes rather handy. Because one definition of equilibrium that I haven't told you yet is that when you reach equilibrium in a reaction, what ends up happening is that the rate forward, right? So this rate forward, K1 times Br2, and the rate backwards, or the reverse rate, K negative 1 times Br to the second power, those two rates equal each other. To you, the reaction looks like has stopped, like nothing else is happening. But what really is taking place is that the Br2 is turning into Br at the same rate at which two Brs are turning back into Br2, and that's happening constantly. So another way to put it is that rate forward equals rate backwards. And in other words, what that also means is that K1 Br2 equals K negative 1 Br to the second power. And if we solve for the intermediate, the monatomic Br intermediate, we have to divide by K negative 1, and we have to take the square root of both sides. And by doing that, we have derived an expression for the intermediate Br, which now we can input into the actual rate law, right? So the rate law is equal to K2 times the concentration of Br times the concentration of H2. So now we input the square root of K1 over K negative 1 times Br2 into the expression, and we end up with the following rate law, which only contains now either reactants or products of the initial reaction. And this is what you want to do in this type of process. You want to make sure that your final rate law ends up having only reactants and or products present in the overall reaction. So be on the lookout for intermediates. You want to get rid of the intermediates from your rate law by substituting in other values. All right, let me give you one more example to finish this discussion. We can have Cl2 reacting with carbon monoxide forming phosgene, Cl2CO. The mechanism has the following three steps. So we have one initial equilibrium, followed by a second equilibrium, and ending with K3. And so you can write the rate forward for the first reaction, Cl2 times M. You can write the rate backwards for the first reaction, M times Cl to the second power. You can write the forward process for the second reaction, K2 times M times CO times Cl. The process backwards, M times ClOCO times K negative 2. And then for the final process, ClCO plus Cl2 times K3. If I tell you that the last step is the slow step, then here you have a few things to do because ClCO is an intermediate. That's not one of the reactants or products in the overall reaction. So you're going to have to use the equilibrium in the second step to substitute for ClCO. So we're going to do that. All right, here we go. So using the first equilibrium that has ClCO present in it in one of the rates, since this is an equilibrium, we're going to equate these two rates to each other. And we're going to solve for ClCO, meaning that M's are going to cancel out. You're going to have K2 divided by K negative 2 times Cl times CO. And that is what can be substituted back into the rate law. And so we do that. The only problem is that we have now introduced a second intermediate that's not present in the overall reaction. So now we need to use the very first equilibrium reaction to get rid of Cl. And now we have rate forward and rate backwards, which are going to equal each other. And we have to solve for Cl. So we have to divide both sides by M. So M's cancel out once again. Divide both sides by K negative 1. And then take the square root at this point. So the concentration of Cl is equal to the square root of K1 over K negative 1 times Cl2. And that's what we substitute back into the rate law. And so you end up getting, an expression that looks kind of funky for the rate constant. But just remember, K3, K2, K negative 2, K1, and K negative 1, they're all constants anyway. So multiplying them together are just going to give you a singular value that you can just call K. And beyond that, though, the part that really matters is your Cl2 to the third half power, right? And it's third half because we had one Cl2 to begin with, but then we introduced Cl2 to the 1/2 power since it was present inside the square root. That's also multiplied by CO. So this thing right here is the proper rate law of the reaction because it only contains reactants and or products present in the overall reaction, right? So we have Cl2 and CO, and if we go back to the original example, Cl2 and CO are indeed reactants of the overall reaction. So this final step right here is the correct rate law for the reaction. All right, so with that being said, we are basically done with this topic. You have some homework in relation to all this material, so hopefully that will go okay. But this is it for kinetics. The next topic we'll talk about will be nuclear chemistry. That relates to some degree to kinetics as well, so you'll see a little bit of an overlap. All right, so see you in the next lecture series.